Start. So today our topic will be linear homogeneous PDE with the constant coefficients, and as in our last video we discussed the case when the right hand side of this homogeneous PDE was 0, but today we'll be discussing the case when the right hand side is a non-zero, right? And recalling from that video what we wrote, that was our differential equation like this: a naught dn a1 d n minus 1 d dash plus dash dash, and last one was a n d dash n operated on z is equal to, the function is g x comma y, and this was our equation number A, right? And we discussed the case when gxy was 0, no, or I should write it as f d comma d dash for this whole operator, and operated on z is equal to g x comma y. That was our last equation number A, right? If gxy equal to 0, then this equation number A reduces to f d comma d dash z equal to 0, and this was the equation number B. All right, and in the last video we solved this equation, right, when the right hand side was 0, but this time the right hand side is a non-zero, so we will be searching the solution for equation number A. Okay, the solution to equation number B, right, is called complementary function, denoted by CF, to equation number A. Any solution to equation A is called particular solution, right, and that is given by z. I am writing that zp equal to 1 upon f d d dash g x comma y is called particular solution. Any solution for this equation that will that value of z that satisfy this equation number 1 precisely for this right hand side term gxy, then that solution is called as particular solution. So we have this time two solutions. One is the complementary function and the other is the particular solution, or we call it particular integral. In short, we write it PS, particular solution, PS, right? Then the sum of these two, complementary function and particular solution, is the complete solution of equation number 1. Then z is equal to complementary function plus this particular solution is complete solution of A, right? So in order to solve this equation number A, we have to find first a complementary function, as we did in our last videos, by putting the right hand side equal to 0, and the new thing is the particular solution, which is found by this zp equal to, I am writing the zp, and generally we write that PS, particular solution, and is found by this way. Notice that this is an operator and it has been brought in the denominator here. See, f d d dash has been brought over here, 1 upon f d d dash. It is treated as a single entity, and any algebra can be done over it. Means you can bring this term anywhere. However, it is an operator, but the good thing about this operator is that it can be brought anywhere in the reciprocal, or you can multiply it by anywhere, and so on. Okay, so we will be focusing on how to find particular solution, right? Okay, now I am writing the method to find the particular solution. Method to find particular solution. Okay. Actually, the particular solution is given by 1 over f dd dash of gxy, and gxy is particularly of the nature some function of ax plus by. Okay. So case 1, if the right hand side gx comma y is equal to phi ax plus by, then this equation A becomes, then equation number A becomes f d dash z equal to phi ax plus by, and the particular solution is then given by this operator can be brought over here, 1 upon f d dash phi ax plus by, right? Okay. And the method says that these the coefficient of x and coefficient of y, replace these d and d dash in the denominator. In place of d, put a, and place of d dash, put b, right? Then a, okay, and ps is given by this is equal to 1 upon f of a comma b phi u, and it will be integrated. One upon f a comma b integrated n times du. This du has been written n times, right? And what is n? N is the order of this f d d dash, means treating it as a polynomial. The degree of this polynomial is n, so integration has to be done n times, right? And that's why I have written du. This is also n times, du n times. Okay, so we'll try to prove this rule. How this rule comes, you have to remember this rule in order to perform a numerical. Now proof of this thing. Proof. My function is phi ax plus by, right? And if I operate d here, d means the derivative, the partial derivative with respect to x, then I will get phi dash and ax plus by and multiplied by a, right? And if I operate d square, then I will be getting a square here, and here it will be phi double dash, right? So on operating the d r times, right, I will get a to the power r and the rth derivative of function phi. Okay. Similarly, and d dash to the power s phi ax plus by will give b to the power s phi, the sth derivative of phi ax plus by. Okay. In general, if I have d to the power r and d dash to the power s phi ax plus by, then I will be getting something like this: ar to the b to the power s phi. Since the order is r plus s, so the derivative will be done r plus s times. Okay, ax plus by. Now this will be the base of this formula, that whatever derivative in terms of d and d dash appears here, on the right hand side we get just d is replaced by a and d dash is replaced by b. You will see that, and the function is replaced by its derivative, right? And the order of the derivative is equal to the sum of these powers, right? So we can write it as or I am writing it as FDD dash, FDD dash, because this is my operator, FDD dash, right? FDD dash of phi ax plus by is equal to a to the power r, b to the power s, no, that will be f a comma b, because d and d dash are replaced by a and b, and phi to the power, I am writing here n. N means, because our operator is of order n, it is an operator corresponding to the nth order PDE. That's why the nth derivative will appear on right hand side. Okay, right. Ax plus by. Okay, so this is what we will be getting from this generalization of this thing. And now, can this operator be taken here 1 over f d d dash, because it is an entity, and f a b can be taken over here, but provided this implies that f d d dash goes here 1 upon f of d d dash operated on phi nth derivative ax plus by is equal to 1 upon f a b phi ax plus by, right? Provided this FAB is not equal to 0. In that case, you cannot bring this FAB in the denominator, right? So this condition has to be mentioned. FAB is not equal to 0 here. We are assuming that case, and this is the nth derivative of phi. This is just phi. If I take the integration to remove this nth derivative, I have to do integration, and integration over here also. Integrating n times, right? And assuming ax plus by equal to b, and assume ax plus by equal to small u, right? I'm writing it as a small u because integration will be done with respect to u. Okay, then this side will become, gives 1 over f d comma d dash, and on integration it's n times, we will have phi ax plus by and 1 upon f a comma b. It is being a constant because fab becomes a constant, so it has to be taken out of the integral, and the symbol of integration will appear n times. And here we have phi, and this is replaced by u, and obviously I have to write du n times. So this is the proof of this formula, right? Okay, so you can see that these a and b takes the value in place of d and d dash, and this function gets integrated n times. What is n? N is the degree of this polynomial, if it is considered as a polynomial, or you can say that the order of the differential derivative, that is n, right? N times. Integration will be done n times, that is equal to the degree of this. Okay, now we'll perform some numericals based on this formula. Example number 1. Okay, solve 2r minus 5s plus 2t equal to some function of ax plus by. Let me take it y minus x. Okay, and this r is actually del square z over del x square, the second order pure derivative with respect to x. S is del square z over del x del y, the mixed second order derivative with respect to x, y, and t is del square z over del y square, the second order derivative with respect to y. Okay, a solution. and see that this right hand side is not equal to 0, y minus x, but we have to take it equal to 0 in order to find the complementary function, right? Then we write auxiliary equation, or we do the factors in terms of d and d dash, whatever way you prefer. I may write as 2d square minus 5d d dash plus 2d dash square, and then this time I have to write z because I am writing d equal to 0. I am taking 0, right? And then factorizing it will become 4, and then 2d gives 2d, that will be minus 4 and minus 1, then 2d and d minus 2d dash, I think, and 2d will be common, minus dd dash plus minus g dash. Okay, now this is correct. Okay, 2d square minus, okay, right, fine, z equal to 0. Then the complementary function, this time we are calling it as complementary function, not the full solution. Complementary function is given by f1 and 2y plus x plus f2 y plus 2x, right? Where f1 and f2 are arbitrary functions. Okay. So this is the complementary function for this equation, right? And now I am going to find the particular solution, right? That is a solution corresponding to this right hand side term, and particular solution is given by 1 over this operator written in terms of d and d dash, that will be 2d square minus 5d d dash plus 2d dash square, and here we have y minus x. And one more thing, do not write this function here because this is an operator that has to be operated on this, so always write the operator first and then comes the function. Okay, now use that rule. So what is n here? N is 2, right? So 1 upon, using that rule, in place of d I will put minus 1 and in place of d dash I will put 1. That will become 2 minus 1 square minus 5 minus 1 into 1 plus 2 1 square, right? And integration should be performed only twice because 2 is the order of this partial order derivative, treated as a polynomial, and y minus x should be replaced by u, and du. I have to mention what is my u, where u is equal to y minus x. Okay, then it will become 2 plus 5 plus 2, 9, 1 by 9, right? And integration of this twice will be 1 u square by 2 and u cube by 6, u cube by 6, and putting this value of u I will get y minus x whole to the power 3 upon 54. So this is our particular solution, and adding these two I will get the full solution. Then z is equal to cf plus pi, means f1 y plus x, 2y plus x plus f2 y plus 2x plus y minus x whole cube upon 54 is complete solution, right? And you can see that this is the order of this PDE is 2. That's why only 2 arbitrary functions appear in the answer. And note that the number of arbitrary functions will appear only in the complementary function. The particular solution or particular integral is a constant free solution. Okay. And one more thing, this solution, why this is called a complementary solution, as the name suggests that, because if I substitute this complementary solution, only this part in this equation, right, then I will get 0 equal to y minus x, means this solution contributes to 0, means it is free, and that's why we call it complementary solution, and means free of cost solution, because it gives 0, right? While this solution is called particular solution, if I substitute this, only this solution here, then I will get y minus x is equal to y minus x, because this solution corresponds to the right hand side y minus x. And if I put the full solution here, then I will again get y minus x equal to y minus x, means the contribution from this complementary function is 0, right? And that's why we call it complementary. Now, taking another example, example number 2. Suppose I take solve. This time I will take d square plus d dash square and z is equal to sine mx cos nx. These mn are constants, right? This time we have a trigonometric function on the right hand side, okay? And see, this is not of the nature as we need, that is phi ax plus by. This has to be converted in that form, some function of ax plus by, right? So writing the equation, taking the right hand side is 0, let d square plus d dash square, or we can follow that method also, as we discussed in our last video, that putting d equal to m and d dash equal to 1, we call that auxiliary equation. Auxiliary equation, that is given by putting d equal to small m and d dash equal to 1 and equal to 0. And remember that this method has some disadvantages also. Use this method, or you can say that this method is preferred when you don't lose the power. Here the power is 2, and similarly the power of this equation in m is 2, means that it is of second degree equation. If in case I lose the degree of equation, suppose this is fourth order equation and here I am getting a second degree polynomial equation, then this method is not preferred, okay? So in this case this is fine, and this gives me m equal to plus minus eta after factorizing it, or you can write it as this way, m plus eta and m minus eta equal to 0, or one may like to write it as, for this, d plus eta d dash and d minus eta d dash, then you have to put z here equal to 0. You can use this or use this directly, okay? Then the complementary function is equal to, for this part, f1, and sign gets changed, y minus eta x, f2, y plus eta x, okay? This is the complementary function, and where f1 and f2 are arbitrary, I am not writing that. Now finding the particular solution equal to 1 over d square plus a d dash square, and here I have sine mx cos nx, but this is not in the form, but I require here. Should I multiply this function by 2 and divide by 2, then it will become like this, 1 by 2, let me put that 2 here, 1 by 2, and this multiplied by 2, okay? Then this will give 2 sin mx cos nx, 2 sin a cos b, and you have to use that formula, 2 sin a cos b, that is equal to sin a plus b plus sin a minus b. Then it will become 1 by 2 d square plus d dash square and sin a plus b. It will become this is mx plus ny, mx plus ny, y. It will become mx plus ny, right, plus sin a minus b plus sin a minus b. So I have got the function in that form, phi of ax plus by. So that will be treated as two different particular solution, one for this and one for this. Okay, then it becomes 1 by 2 1 upon d square plus d dash square sine mx plus ny plus 1 upon d square plus d dash square sine mx minus ny, right? Okay, then applying the formula for these two functions, one is sine mx plus ny and one is sine mx minus ny. See the degree of this polynomial, that is equal to 2, so it has to be integrated twice. First thing is that, and it becomes sine u du, right? This has been taken as u, and here we will have 1 upon m square plus n square, d is replaced by m and d dash is replaced by n, and I have to mention what is my u. I will mention that here, plus 1 upon m square plus minus n square. Okay, integrating it twice, sine, let me write it v dv, where I have to mention that mx plus ny equal to small u and mx minus ny equal to small v, right? One by 2 in performing integration, sine u integrated twice will become, one time it will become minus cos u and then again minus sine u. Then it will become 1 upon m square plus n square and minus times of sine u, right? And what is the value of u? U is mx plus ny. Should I put this minus here? Minus. Okay. Similarly, integrating that, I will get minus 1 upon m square minus n square, and here I will have sine mx minus ny. Okay. So this is the answer. I think we can take minus common, minus 1 by, oh, this will be m square plus n square. Okay, right. Then m square plus n square can be taken out. Minus 1 by 2 m square plus n square, and we have sine this plus sine that. Sine c plus sine d should be applied. In the bracket we have sine mx plus ny plus sine mx minus ny, means we have to use the formula of sine c plus sine d, and that is 2 sine c plus d by 2 into cos c minus d by 2. You have to apply that formula from trigonometry. 2 sine c plus d by 2, this plus this by 2, that will give me mx multiplied by cos c minus d by 2, and that will give me ny, right? And 2 and 2 will be cancelled. I should write that formula using the formula, use this formula, sine c plus sine d equal to 2 sine c plus d by 2 into cos c minus d by 2. This is the formula I have used. Okay, right. And 2 will be cancelled, right? And then I will be getting something like sine mx cos ny upon m square plus n square. So this is my particular solution. Then complete solution is given by z equal to complementary function. This was the complementary function, f1 y minus eta x plus f2 y plus eta x plus this particular solution sine mx cos ny upon m square plus n square. This is a complete solution. Is complete solution. Okay, so far we have discussed two types of examples. One is the simply function of ax plus by, means y minus x, and the second example we had trigonometric function. Okay, on third example we will take some exponential function e to the power ax plus by type. Let me write example number 3. solve d cube minus 6 d square d dash plus 11 d dash square minus 6 d dash cube z is equal to e to the power, suppose I take 1, 2, 3, 2x plus 3y. Okay, so this time we are having exponential function on right hand side. Solution, auxiliary equation m cube minus 6m square plus 11m minus 6 equal to 0, right? So this is a cubic equation, and searching for its factors, I will guess some root. See this constant, this is 6, and the divisors of 6 are plus minus 1, plus minus 2, and plus minus 3. So I have 6 integers which may be the root of this equation. I will start with m equal to plus 1, and I see that putting m equal to 1 will give 0, because 1 minus 6 plus 11 minus 6 is equal to 0. It indicates that m is equal to 1 is one of the root of this equation. Okay, right? And let me try with minus 1, but definitely minus 1 will not be its root, because that will give all terms negative. My putting m equal to minus 1 will produce this negative, this term will be negative, this will be negative, negative, and ultimately a negative sum will be there. So I will not be getting that equal to 0. So m equal to negative root is not possible for this case. You can see the fluctuations in sign. And putting m equal to 2, yes, if I put m equal to 2 here, then 8, that will be 8, and plus 22, 30, and this will be minus 24 minus 6 minus 30, and that is equal to 0. Means that by hit and trial method we find two of its roots, m equal to 1 and m equal to 2. Okay, then if m equal to 1 and m equal to 2 are its two roots, then what will be its third root? And for that, a very simple thing is that, again, the product of root, or you can say that the sum of roots, means if the third root be alpha, right? We already have two roots, one is 1, second is 2, and let the third root be alpha. The sum of the roots should be equal to this number 6, right? Okay, then 1 plus 2 plus alpha is equal to 6, and that gives me alpha equal to 3. So by inspection I have found all of its roots. There are 1, 2, and 3. I'm writing it at directly by inspection. Obviously, the inspection, by saying that inspection, what I did, you remember that by inspection we find that m equal to 1 and 2, I found these roots by trial. Okay, and after that I applied that sum of roots is equal to 6, and that gives me 3. So these are the roots of equation m equal to 1, 2, 3, and they all are distinct roots. Therefore, the complementary function CF equal to, since the roots are distinct, I will write it as f1 y plus x, f2 y plus 2x, f3 y plus 3x. So this is the complementary function. f1, f2, f3 are arbitrary. Now, particular solution is equal to 1 upon d cube minus 6d square d dash plus 11d d dash square minus 6d dash cube, and here we have e to the power 2x plus 3y, right? So it will be integrated size, because 3 is the degree of this polynomial if taken as a polynomial in M, and I have to put d is equal to 2 and d dash equal to 3. But putting d equal to 2 and d dash equal to 3 here will be complicated, because I will get some d square and d dash square like terms. So I will prefer to write this as, because I know that these are the factors, so I should write it as d minus 1d dash, d minus 2d dash, and d minus 3d dash. right, in order to ease the calculation. And then now it is simple, putting d equal to 2 and d dash equal to 3, the calculation becomes easy. That will become 2 minus 3 into 2 minus 6 and 2 minus 9. Okay, integrating it thrice, e to the power, this is taken as u du du du, where u is equal to 2x plus 3y, right? And this will be minus 1 into minus 4, that is plus 4, into minus 7, minus 28, minus 1 upon 28, right? And integration of e to the power u thrice will give me e to the power u, and u is replaced by 2x plus 3y. Then the solution will be z is equal to f1 y plus x, f2 y plus 2x, f3 y plus 3x minus 1 by 28 e to the power 2x plus 3y is the solution. Okay, so this is the example for an exponential function present on the right hand side. Now taking some another kind of example, example number 4. Solve r plus s minus 2t is equal to, let me take something like roots will be d minus 1 minus 2. Okay, right, let me take it as 3x plus 2y. Okay, and I will take power as 1 upon 3. Right, solution, writing its auxiliary equation in m, that will be m square plus m minus 2 is equal to 0. That will give me minus 2, I need minus 2, and 2m minus 1, m minus 1 into m plus 2 equal to 0, right? Okay, correct. Then I will get m equal to 1 and m equal to minus 2. So roots are distinct. So complementary function will become f1 y plus x, f2 y minus 2x, where f1 and f2 are arbitrary functions. Now finding its particular solution, 1 upon d square plus d minus 2, and here we have 3x plus 2y to the power 1 by 3. Okay, sorry, this is d square d dash minus 2 d dash square. Okay, now here n is equal to 2, it will become is equal to 1 upon, putting d equal to 3 and d dash equal to 2 here, I will get 3 square plus 3 into 2 minus 2 into 2 square. Okay, and integrating it twice, it will become u to the power 1 by 3 du du, where u is equal to 3x plus 2y. That will become 9 minus 8 1 and 6 7, 1 by 7 equal to 1 by 7, and integrating it twice, integrating it once will give u to the power 1 by 4 by 3, u to the power 4 by 3, and 4 by 3 in the denominator, that will appear here 3 by 4 du. Okay, now integrating it again, become 3 upon 28. Integrating it again will produce u to the power 4 by 3 plus 1 will give 7 by 3, and we will have 3 by 7. Okay, and it will become 9 uh, 56, 70, 14, 196, and u to the power 7 by 3. And what is the value of u? U is actually 3x plus 2y, 3x plus 2y to the power 7 by 3. Okay, so this is the particular solution, and notice that we do not write the constant of integration. We are performing integration, but we don't write the constant of integration because we are finding the complementary, we are finding the particular solution, and particular solution do not contain any arbitrary constant because all arbitrary constants or functions are involved in the complementary function part, right? So you need not to write the constant here. Okay. So therefore z is equal to f1 y plus x plus f2 y minus 2x plus 9 upon 196 3x plus 2y 7 by 3 is complete solution. Okay, so far we have done 4 cases, and maybe right hand side the case where ax plus by, or we can say that is simply pure function of x or pure function of y. Let me take example number 5, where we will be dealing with d to the power 4 and okay, d to the power 4 plus d dash to the power 4 and z. Suppose I take only x here, right? Means y is absent. It can be treated as 1x plus 0y, right? Where b is equal to 0. Okay, and again the left hand side is complicated solution. Let me write the auxiliary equation first. Auxiliary equation in m, putting d equal to m and d dash equal to 1, and remembering that by doing so we don't lose any degree because this is the 4th order PDE, and obviously the auxiliary equation is of 4 degrees, so everything is fine here. And trying to factorize it because m to the power 4 plus 1 cannot be factored in real roots, so we have to use some complex number theory here. Writing it as m to the power 4 equal to minus 1, that is fine. Okay, and if I take this 4 as 1 by 4 here, okay, fine, and that will give me m is equal to minus 1 can be written as cos, okay, sine, that will be 0, cos pi plus eta sine pi, or I can write it as odd multiples. Minus 1 is actually, minus 1 can be written as minus 1 plus iota dot 0, means minus 1 plus iota 0. I will write that minus 1 plus iota times 0 and 1 by 4. Now this minus 1 is taken by cos, and 0 is the value given by sine, and we know that the cos with an odd multiple of pi gives minus 1. So cos pi is equal to minus 1, cos 3 pi equal to minus 1, and so on. So in general I will write cos 2k plus 1 pi, that is the odd multiple of pi, remember that, and here I will write iota sine 2k plus 1 pi 1 by 4, and what is my k? K is equal to 0, 1, 2, 3. Remember that I will be getting only 4 roots, and you have to restrict yourself to only 4 values of k. First 4 values of k starting from 0, 1, 2, 3. These are the 4 values, right? Because we will be going to obtain 4 roots only. Okay. Now substitute the first value of k equal to 0 here. No. Minus 1 plus 0 iota. Okay, that will be a complex number. M equal to, and this 1 by 4 goes here, this will become cos 2k plus 1 by 4 pi plus iota sine 2k plus 1 by 4 pi. By using that De Moivre's formula, that power goes in the angle, right? Then putting k is equal to these values, I will get m is equal to putting k equal to 0 here, I will get cos pi by 4 plus eta sin pi by 4. For k equal to 0, I will get cos pi by 4 eta sin pi by 4. That will be cos pi by 4 is equal to 1 by root 2, 1 by root 2 plus eta sin 1 plus eta 1 by root 2. This is my first answer for k equal to 0. And implies m equal to, next value of k is 1, put k equal to 1 here, I will get cos 3 pi by 4 pi plus eta sin 3 pi by 4, and the 3 pi by 4 means pi minus pi by 4. I will write that cos 3 pi by 4 plus eta sin 3 pi by 4, and that will fall in, I think, second quadrant. 3 pi by 4, right? Pi by 4 is 45 and multiplied by 3, yeah, second quadrant. And in second quadrant, cos is negative, sin is positive, so the answer will be minus 1 by root 2 plus eta 1 by root 2. Okay, fine. This is for k equal to 1. Similarly, for k equal to 2, I will get 5 pi by 4, and 5 pi by 4 will fall in third quadrant. Yes. Pi plus pi by 4, right? Third quadrant. In third quadrant, cos is positive and sin is negative. M is equal to cos is positive and sin is negative. No, both are negative. Cos is and as well as sin are negative in third quadrant. So I will write minus 1 by root 2 minus eta 1 by root 2. This is for k equal to 2. And the last value, m equal to, that will fall in obviously fourth quadrant. Putting m equal to k equal to 3 here. 7 pi by 4, that will be 2 pi minus pi by 4. Yeah, fourth quadrant. And fourth quadrant, cos is positive, sin is negative, right? So I will be getting 1 by root 2 and minus eta 1 by root 2 for k equal to 3. So I've got 4 values of m, and since all of them are distinct, writing the complementary function that will consist of 4 arbitrary functions. Therefore, complementary function is equal to f1 first root y plus, I will write it as m1, m2, m3, m4. Okay, m1, m2, m3, m4, y plus m1x, y plus m2x, y plus m3x, y plus m4x, where all m1, m2, m3, m4, okay, I can write it as mi, I running from 1, 2, 3, 4 are given by equation number 1. Let me call it 1. Right. Okay. So m1, m2, m3, m4 will be taken from here, and this is a complementary function containing 4 arbitrary functions. Now finding its particular integral, pi equal to 1 upon d to the power 4 plus d dash to the power 4, and here we have x, or it can thought of as 1x plus 0y. That's very simple. So putting d equal to 1 and d dash equal to 0, I will get 1 to the power 4 plus 0 obviously, and I have to integrate it 4 times, u du 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 du, where u is equal to x, 1x plus 0y, or simply x. So that will be 1 in the denominator, and perform an integration 4 times, one time u square by 2, then u cube by u square by 2, u cube by 6, or factorial 3 factorial, and u to the power 4 by 4 factorial, and u to the power 5 by 5 factorial. So answer will be u to the power 5 by 5 factorial, or 120, right? Okay. And putting the value of u again, which is x to the power 5 upon 1 to 0, therefore z is equal to f1 y plus m1x plus f2 y plus m2x plus f3 y plus m3x f4 y plus m4x plus x to the power 5 over 1 to 0, where mi is I equal to 0 1, no, not 0 1 2 3, 1 2 3 4, 1 2 3 4 are given by equation number 1. So this is the complete solution, is complete solution. Okay, so we have discussed almost all of the cases. On the right hand side is the function of x plus by, and in the next video we will be taking some more examples, maybe of some different type. On the right hand side is some function, product function of x to the power m or y to the power n, in the next video. So for this video, thank you so much.